Okay, so I'm very happy to welcome Christine Harrison, who's a research scientist at Lawrence Berkeley National Lab and specializes in doing high-performance computing to design better batteries. So maybe we'll find out what happened in the Dreamline.
Thanks, Jim. Yeah, I'll talk a little bit about that. Just for full disclosure, I'll just say I'm a material scientist with physics background, and high-performance computing is what I use to sort of get the job done. So I'm not a computer scientist, but I'll talk a little bit about that stuff. If you probe me too deeply, I will not be able to answer the questions. So I'll be talking about accelerated materials design through high-throughput first principles calculations and data mining. And my outline of my talk is that I'll give a motivation for why we're doing this, why we're using computations to design new and better materials. And then I'll give you a very short crash course on density functional theory, which is our workhorse. That's how we solve the Schrödinger equation. Then I'll talk about all the problems we have when we try to run these codes on high-performance computing centers, and we haven't solved these problems yet. We actually have a group of students working on one aspect of the problem, so I'll just mention that. We are working around it. So let's say that we solve the computing. I'm going to give you some examples of how we've done this before using assigned clusters, so not shared resources, which is a lot easier from our point of view, but not as efficient if you look from a global perspective. And at the end, I'll talk about what this has evolved into, which is called the Materials Project, which is a growing resource, and it's a public resource both in terms of codes and data. So let's start with the motivation. There are a lot of applications around us that are critically dependent on materials. This is one of them. The reason that you don't see a lot of those fuel cell-driven cars out there, right now it's more about lithium-ion than fuel cells, but fuel cells used to be the big thing, and people thought we're going to have these cars with fuel cells in them very shortly. We don't, and one of the reasons, the primary reason, is actually that the catalyst that enables the oxygen reduction that is needed for a fuel cell to work is the best one out there is platinum. And a catalyst works on surface reactions. So the smaller the particles you make, the more efficiency you get, because it only happens at the surface. You want a lot of surface area. The problem with these catalysts, that you can see down here, if I can get the pointer to work, here we go. This is what we call a Pourbaix diagram. It tells you about the stability of things in water. Here's the hydrogen potential versus, now my pointer disappeared again. Okay, this is the hydrogen potential, and this is the pH, and this is a little platinum nanoparticle, which is what they have in these fuel cells. And platinum tends to be very noble if you have a big bulk of it. It actually resists most of the dissolution force in normal, even at pH 0, which is as low as you can get pretty much. We can even go down to -2, but then you have more protons in your bath than water. So the pH scale kind of breaks down. This is the dissolution region you get if you have a 2 nanometer platinum particle. So, if you go from a bulk system that actually works, but you have not a lot of surface area, to a small particle where you have a lot of surface area, you start dissolving these particles. They're not stable anymore in very acid electrolytes. And they haven't found a reason or a way to get around this. This is the main reason that these cars only work for a bit, and then you have to reposition, platinum in your fuel cell, which is very expensive, so it's not going to work. Photovoltaics, that kind of works, right? We have it all around. I actually had it on my roof in Orinda. The problem is that the material that we tend to use is silicon. Silicon isn't the greatest material, but it is the one that works the best right now because we are very good at engineering it. This is the amount of cost per plate or per panel that is not related to the material at all. It's all the other stuff that goes around, the transparent conductor that goes on top of the photovoltaic. It's the panel itself. So you can imagine that if you make a better material, you get more bang for your buck, because this is kind of almost fixed. Yes, you can make it a little bit better. This is, I think, this is from international sources. This is domestic. So you can make it a little bit better or cheaper. But if you have a material that works better than those 12% or whatever that silicon does, then you have a more efficient panel. So again, it's about the material. Okay, I'm totally dating myself by putting up these pictures, but you know, this was one of my favorite movies. How many of you have actually seen it? All right, yes, I like this. Doc fuels his DeLorean, and this is actually a quote from the movie. No, this sucker's electrical, but I need a nuclear reaction to generate the power that, you know, in order to drive the vehicle. This, believe it or not, is an electric DeLorean, 2012. Somebody watched that movie and really wanted to make it happen. But anyway, the problem is, of course, that so the electric cars that we see out there, the, you know, PHEVs, EVs, all those different varieties of it, they all tend to go to lithium-ion. That's the technology that kind of works today. But again, 70 to 80% of the cell cost is materials, and it's not just the active material, even though that's an important part of it too. It's the, you know, it's the can, it's the electrolyte, it's the separator, believe it or not, which is just a piece of plastic with holes in it. So if you get a better cathode and anode, that gives you a lot of leverage, because those are the active components. Those are the ones that give you the kilowatt hours that you need. So again, a materials problem. Okay, politics, also a materials, or materials can play a role in politics. You may not remember this, is like 2.5 years ago, but in September of 2010, Japan arrested a Chinese boat captain that was sort of floundering around on the seas where, you know, nobody really knows is this Japan or China Sea. But, you know, Japan thought it's ours, so you're trespassing. Now, China has all the mining of rare earths in the world. And rare earths are very, very critical components in some of our applications. For example, in electric motors that go into those cars that in order to get, you know, electric drivetrain to work, we need an electric motor. And Japan has no domestic way of getting rare earths. Actually, today, the US doesn't either. We just reopened the mine here in California, Molycor. For the last 5 years, we didn't have any production either. So we are all dependent on China for these materials. What do you think happened? 2 days later, they released the boat captain. But, you know, the Japanese are smart, right? They don't want to be dependent on China. So they actually started right away investing in induction motors, which don't use rare earths. And they don't use these permanent magnets that rare earths enable. And I think in 2011, they announced that we are now ready to use these induction motors. But that's just one example. Rare earths are used in a lot of different things. And it's been we've actually had even a sort of a large research initiative here in the US that was recently launched for critical materials innovation. So again, a materials problem that is causing even political ramifications. So if we want new materials, we want better materials. We want, you know, better PVs, better lithium-ion cathodes and anodes. We want, you know, another catalyst for the fuel cell. We want a substitution for rare earths. What do? We have to design new materials. It's not easy, unfortunately. This is a study done by Eager in 1995, and you would think that, well, we've gotten so much better at it. It was recently redone, and it's still the same. It takes about 15 to 18 years from a material working in the lab to being commercially successful. And you would think that that's a really long time. It's from working in the lab. It's not when I come up with an idea and I try to make it and it kind of doesn't work and, you know, 3-4 years down the line it works. No, it's from it working in the lab to being commercially successful. And do you know why? It's not, I wouldn't have come up with it. It's because, according at least to Eager, and I think we're all kind of agreeing when we look at the data, it's because we don't have enough information about the materials. When people design and invent new materials, which is hard enough as it is, they test a few properties. They don't test everything that's going to be relevant in order to make that material actually commercially viable. They don't look too much at the cost. They don't look too much whether it's going to last 10 years. They don't look whether it's temperature stable at the absolute sort of range of temperatures that's going to be relevant. Take lithium-ion batteries, for example. They have to work from -20 to +30. And now they're putting cooling devices on these things when they go out into the Arizona desert because, you know, they are going to degrade the battery significantly if they stand around in 30 degrees Celsius. We know that, but, you know, it's not something we optimize for. So when people then bring these materials that kind of work or have a few properties that are really good to an industry, they have to engineer around it. They have to find these cooling devices, they have to do other things, they have to change the material, they have to coat it. You know, the platinum catalyst, they tried a lot of different things, like coating it, for example, with different other materials that would resist this acid dissolution. It didn't work. In some cases it works, in some cases they find something to sort of mitigate the problem. In some cases, they don't. And that's what takes these 15 to 18 years. So if we're able to sort of chart out the materials better, if we can find more, if we can optimize or chart out the properties of the materials better up front, so we can do a more global optimization, we could avoid these 15 years. If we knew more about the material, if we knew that this is going to be really great from this perspective, but it's going to be really horrible from this perspective, and it's really the weakest link that sinks you. You would rather choose a material that does sort of average on all properties rather than scores really high on something but really terrible on something else. Because if you can't engineer away that, you're screwed. So if we can get more information about the materials, we could do better. So how do we compute? So one of the things we could do then, we could compute properties. Because measuring them all is really hard. And people aren't going to do it. So one way of doing it is using quantum mechanics. And this is just a typical thing. One thing we can do, we can compute band gaps. Does that really help us? Because we really want engineering properties. We want things like dissolution, corrosion, stability, things that matter for the people in the industry. And unfortunately, there isn't really a quantum operator that is just give me a better battery. So you have to calculate all these different properties, and you have to then analyze them and put them together and see that it actually works. But there are ways of doing it, and I'm going to show you a bit about how to do that. So let's go into the next section of the lecture, which is how do we combine computational material science and first principles calculations, which is this crash course in density functional theory. So we're starting from the atomic numbers of the periodic table. This is what we have. And we want to do this from first principles, which means that we have no experimental input. We want to do it the Schrödinger equation way, not be reliant, because that's how we get predictive power. So we want to solve the quantum mechanical equations for the material and predict the physical and chemical properties of the system. And this is really the equation we want to do, the time-independent Schrödinger equation. Yes, this is nice to know what happens with time too, but this is the good starting point. And it's an eigenvalue problem. You guys are, solve these stuff all the time. It's a steady state problem, and let's see what we can do about it. There are two kinds of particles that are involved in this equation, the electrons and the nuclei. And if we write it out as a function of both of them, and this is the nuclei position, and my cursor always seems, here we go, and the electron positions, and then the energy of the electrons, and the Hamiltonian of both of the particles. The Hamiltonian tells you about the interactions, the kinetic energy, the potential energy that comes from the interaction between the different particles, and then the energy of the system as a function of all these parameters. So if you look at what the Hamiltonian contains, it's the kinetic energy for both the nuclei and the electrons. It's the interaction between the nuclei. It's the interaction between the nuclei and the electrons, and then, of course, symmetrically, it's the interaction between the electrons and the electrons. You just basically write out every single term that contributes to the energy of the system. One of the most famous and the beginning approximation we do is that we say that the nuclei moves really slowly compared to the electrons. If you were to move the nuclei a little bit, the electrons immediately find their steady state ground state for that new position. So we separate out the nuclei. Separable variables, we make another partial differential equation just for the nuclei themselves. And then we look at the electrons and how they interact with the rest of the system. The electrons are the tricky ones. There's tons of them. And they have all these nasty interactions that we're not very good at. We know what they are, but they're very hard to categorize. So the mathematical difficulty, the numerical difficulty of solving the Schrödinger equation increases as a function of, is exponential with the number of electrons. With modern supercomputers, we can solve this system exactly, because we know exactly what all these interactions are. It's a Pauli exclusion principle, all those quantum mechanical things where the electrons can't occupy spaces too close to each other. We can solve this exactly for about 4 to 5 electrons. And a typical solid contains 10 to the 20 electrons. So it's not feasible to solve this exactly. We have to come up with an approximation. And this is where density functional theory comes in. It's actually an exact theory, but it enables a very, very smart approximation. So you start with, again, the Hamiltonian, and we've now separated out the nucleus part. So we now have the electrons that are living in the bath of the potential from the nuclei that are in their fixed position from the electron point of view. And we're dealing with this term here that is the difficult one, because that's the electron-electron interaction. That's where all those quantum mechanical effect comes in. And instead of casting that as a many-body problem, we look at each electron by itself, and we say it lives in the potential of the other electrons. And if we can approximate that term and make it local, make it only dependent on where you sit, and not all the other, as this electron, and not all the other terms or positions or radii that exist, then it becomes a solvable problem and much more efficient. That's called a local density approximation, and that was really what sort of enabled the density functional theory to become as successful as it was. If you look at it physically, what we do is that we take a homogeneous electron gas and we solve for a potential for a homogeneous electron gas, and we take all the tricky part of the electron-electron interactions from that very simple system and take every single system that we have and cast those terms from a homogeneous electron gas problem. That doesn't sound like it's going to work, right? I mean, all these systems out there, all these crystals and materials that we have, they're not homogeneous electron gases, but it turns out from a local perspective, it's not such a bad guess. When people came up with this approximation, they thought, no way is this going to work. It's just sort of a prototype, something we can show for maybe a few systems that are very well behaved, but it actually works much better than you would think. These are some of the properties that I've been involved in that I typically calculate on a run-of-the-mill day when I do my materials design optimizations. We can do phase diagrams. This is a ternary phase diagram that involves one of those battery chemistries that we talked about. This is lithium, iron, phosphate, oxygen, which contains one of the most famous cathodes in the lithium-ion world, which is the olivine lithium iron phosphate. This is diffusion of ions. This is voltages for cathodes. This is particle morphologies. If you try to make a material, they tend to crystallize in different forms. We can predict that. These are band gaps, reaction enthalpies, releasing oxygen as a function of temperature, which is really important for safety, and I'll get to that later. So a lot of these materials properties that are now real engineering properties, their voltages, their safety, their diffusion, can actually be calculated using this very simplified version of the Schrödinger equation. And of course, if we can compute all these cool properties, and if we have a really large cluster at our disposal, then we can do a lot of materials, which is where the synergy between having a lot of computers and a robust theory that actually works, then suddenly you can predict properties of a lot of materials. And you can start to chart out those spaces that are interesting from a materials design perspective, and maybe you can actually help people make better materials. So let's go to the high throughput scientific computing part. So now we have the tool and we have the vision. Let's say we had tons of computing at our disposal. What would we do? So it turns out that these DFT codes that I just said were so great, they're trivially parallelizable over k-points. That's how we solve our problem in k-space. In the reciprocal space, we don't solve them in real space typically. But so it really is easy to do that. Even I have written a code that parallelizes a code over k-points. But every time you've solved for all the k-points, you have to bring all that information back and consolidate it until you spit it out on the k-points again on the grid. And this happens hundreds of times per calculation. It's too much communication for a normal of these sort of high-performance computing centers to handle, and it slows down the whole calculation tremendously. No DFT code that I know of scales better than 30 to 40 nodes, which isn't acceptable if you're going to use, you want to use half of Hopper, which I don't know. Jim, could you say how much half of Hopper is?
Close to 100,000.
Yeah, 100,000. So think about it. That's where you want to get. You want to scale your problem to 100,000 nodes, and we're up to 30. It really isn't. It's not. And this is where computing is going. If you look at where the money is going, exascale computing is important. That's where all the money. So I can't fit my problem I can't cast it. And I'll tell you some of the things that we're doing and the problems we're having. Another problem that we're having. So we can't parallelize it well. Well, if you can't parallelize it well, then you can spit out a few. You can put out your calculations on a few nodes, but you need lots of them then, right? You need 250 jobs over each 30 nodes, then at least you're getting something done. You still have to work with the fact you have to predict how long are they going to take Typically, we like these jobs to take a few minutes, an hour, 2 hours. That's, again, how these supercomputing centers work. Lots of cores for very short time. That's what they're optimized for. This is, I think, how many of these? I don't know how many this is. This is 50,000 DFT simulations, right? And the number of electrons per number of atoms, which we tend to think that correlates with how long it would take to solve the problem. That tells you something about the complexity. And the color scale here is how long it took to solve the problem. So the red is weeks, and the pink, magenta, is minutes. And you would think that this region here would be all magenta, and this region out here would be all red. But no, they're red down here. There are a very small system that takes weeks to solve, and there are a very large system that only takes a day. So it's really hard to find a way to sort of predict just by using two very simple but still intuitive metrics on how long a job is going to take. So not only don't we parallelize well, we also don't have a good way of predicting how long it's going to take to finish. So another kind of similar plot, which tells you the time of the simulation and the run number. And this, again, are statistics, those 50K DFT runs. And you can see they're all over the place. And if we sort them, we see that, yes, a lot of them will take around here, but there are those that take a really long time and those that take a short time. So in all these scripts, I have to ask for an upper band.
Are those all the same job?
No.
So they're different materials?
Yes, different materials. So it's that's typically how we do it. We submit maybe 2,000 materials to run. It can be slightly in the same chemistry space, but they can be very different structures, for example. And some structures have more complexity to them than others. That's one of the parameters that we're looking at to understand this or to be able to predict this better. And if it doesn't finish within your wall time, you have to restart it, and that's inefficiency. It takes time to restart it, and it would be much better if it finished. There is sort of we are working on doing a stop-start version of it, but it's not something that we like to do. So this is just an example of what one of my collaborators is doing. He has some students to look at he had downloaded from our database 2,000 of our materials to start with, just as a test set, and try to look at all the different parameters that they could, not just number of electrons and atoms, but also the structure, the symmetry of the structure, things like that, and see if they can find a way to predict the time it would take to finish. And they're up to about 85% accuracy, so we're excited to see if we can actually test that soon. But I haven't tested it yet, so I'm not quite sure if that's true or if it's going to work for more than those 2,000. But at least it gives you an idea what you can do in this space as a student.
And just SVN is a support vector machine, which is a typical machine learning algorithm.
So maybe I missed this. What are the kinds of features that you feed into the SVM? Do you tell it about, here's what's about this job?
So I don't know. I'm not the head of this particular project, but I'd be happy to forward your question to the guy who's in charge of it. Yeah.
Thanks.
I can just imagine what they're doing. They're probably feeding in a lot of stuff. I mean, if I know machine learning well, it's everything from the things that actually don't correlate at all. You usually don't pick from the beginning, right? You suggest a number of different parameters, and some of them correlate and some of them don't.
I had another question with regards to the SVM. So can you identify the slowdown before you run the simulation, or is this on the fly telling you that these workers are going to be slow? Is it a dynamic notification, or are you predicting offline?
We have to do it beforehand, because you submit to the cluster with a certain wall time. So what you give the algorithm is the unit cell with the symmetry and the number of atoms and the electrons. And the chemistry. That's all you can do. And then you need an estimate. How long is this going to take? Okay. So that you can then, so it can't be, I mean, I could imagine that if you were to do it dynamically, that might be worth something, because if you start looking at a simulation and you're seeing that it's not going as fast as you would like it to go, then you can sort of give up on a certain number of them. Yeah.
Or you could load balance another thing. Yeah. Another question is, when you talked about electrons and atoms being directly related to the amount of computation time, do those have different relationships depending on the material that you're looking at?
Yes. Okay. Yes. Some of them are more tricky than others. Some of them have, for example, d electrons are tougher than s electrons, so it depends on which material you're looking at and how many of those they have and how many of them, which d electrons are interacting with other d electrons. So yes, depends on the chemistry, the structure, the number of atoms, the number of electrons, so all this.
Okay, and the force between them?
Yeah,
Okay.
yeah. So that's sort of structure dependent. If you're very close or if you're far away, and what kind of interactions are you dealing with?
Okay, because I worked with lamps from San Diego
Yeah,
for a bit, and
yeah.
it was very hard to get complete information for all the parameters spaced. So I was wondering what was the intuition behind that.
Right, yeah, no,
so
no,
that
it's-
answers it.
Yeah, okay, good. Yeah, so LAMPS is a classical code. So you're basically just doing optimization on the electrostatics, so not the quantum mechanical. But yes, it does come into a lot of the stuff that we do is also electrostatics. So yeah. So just to sort of summarize what we're dealing with here in high throughput materials computing, we want to run large numbers of jobs at a variable duration time, which is completely the inverse of what most typical high throughput clusters are designed for.
So will you come back later and tell us what the obstacles to parallelization are? I mean, why does it stop at 30 and what's needed?
As far as I know, and again, I haven't looked at this problem myself in a long time, but clearly nobody else has been able to solve it either. It's communication. That's the problem. And I don't know if you can build a specific cluster for that, but nobody does, right? Yeah. So high throughput computing comes down to two concepts. Basically concurrency, how many cores can I use? And again, we are in this particular case, we're limited to 30 or 40, otherwise we start losing time. And policy, for how long do I have to run and what groupings can I use? If you have a local resource, and this is typically where most of my colleagues go, they actually buy their own cluster so that they can use it for a month or 2 months because they don't want to deal with wall times. They don't want to deal with the shared policy problems that we end up in. And if you only people who are doing other kinds of codes like quantum Monte Carlo typically go to these shared resources because they are better suited for them. With our DFT codes, we tend to run them on our own. If you are using a shared resource, and in our particular case, we wanted to do this because we wanted to do more materials than anyone had ever done before and more properties than anyone had ever done before, so we really didn't want to buy a 10 million cluster. That wasn't sort of part of our strategy. So we wanted to make this work on what was available. So then you have to map a workflow onto the policy. You have to look at the policy and see what you can do. In shared resources, long, small jobs and short, large jobs are natural enemies. This is a particular graph from NERSC where you can see the number of cores as a function of the time and their scheduling. And I don't know if any one of you have worked on the sort of optimization of fitting these different jobs into a shared resource. I mean, I just look at that and I go like, man, that's pretty cool and it's complex and I understand why they have the policies they have. Because if you want to have a 90% efficiency of your cluster, you want to report that we are using our cluster as much as we can, then certain jobs are enemies to that. If efficiency is one of your performance metrics, then you, for example, this guy here is a problem, right? The guy who asked for a ton of cores for a short time, because you have to shut down everything for a while. All these other jobs have to stop in order to accommodate that dude. And we would be this dude. A long tail of few cores for a long time. And that doesn't even show up, right? Because when I submit that kind of job on Hopper or some of the big, they just say, you're going to wait forever. It's never going to happen. And I want to do that for 250 jobs or 300 jobs or 1,000 jobs, and I want to have only 30 cores each, and I want to have it for 2 weeks. That takes a really long time, and I wait forever. So it's a tough one. But of course, like you can get mad for a bit, but eventually you just have to start working around and see what you can do. This is kind of the same. This is the same plot. You wait a long time to get these outlying jobs, and again, these are the jobs that are naturally accommodated because there are lots of cores for a short time. We will be few cores for a long time. So if you need to do lots of run jobs, what do you do, right? It doesn't match with the job scheduling policies. You can consider, for example, consolidation. Can we bunch them together? You can write scripts for that. We've done that. That works to some degree. But then you have to make sure that you bunch them so that they all kind of take the same time, because otherwise some of your worker bees are idle. And then we come back to that problem of predicting how long each job will take up front. And And optimization always often requires consolidating tasks. You can do A in sequence and B and C, but that tends to get even worse for us because we take a long time as it is. So last year we got 10 million CPU hours at NERSC, which we were very, very happy about, and we were like, oh my God, here we go. This is a Gartner hype cycle. I don't know if you've seen it before. It's a typical cycle what people go through when they got a happy news, and they go like, oh, we're going to run everything. So we got that in January last year, 10 million CPU hours. Do you know when we were up running and actually crunching through these? June. Because we had to work through all these issues that I've been telling you about, and we ended up here, where half of my team were tearing their hair, and one of them had hair down to here, because he's from Berkeley. But then after a while, we actually did solve some of the issues, and we came up and we did run through the 10 million CPU hours by October. So it's doable, but it requires a lot of work. And some of that work is people time. Where am I going to put my effort? So we actually ended up writing an entire workflow to keep track of our jobs, to submit them in a reasonable manner, to keep, so when they didn't finish, pull them back into a database, analyze how far they went along, and then resubmit them with some estimate of time that made sense. So we wrote a whole workflow basically to manage this fact that we were dealing with a shared resource and that we had to get around it. Plus, NERSC worked with us as well and opened up the number of jobs we could ask for. We actually had a special queue for a while where we could submit 250 jobs until other people saw there was a special queue, and then they wanted to get in there too. Lesson to self, never call it a special queue. Call it the dumb queue or something. I wasn't very smart. But it's a good lesson to think about how you have to then, we went from January to June in writing scripts and codes to accommodate the shared resource. That was time. It was time well spent because now we can actually use it in a better way. But it's this sort of like, trade-off between people's and coding time and what you actually can do on your cluster. There are a lot of different things you can look at and accommodate, different flexibilities. You can look at your resource and see the charge factors. You pay more to get in quickly.
Hey, just while we're thinking about all this kind of queue optimization and how to get the best bang for your buck kind of thing.
Yeah.
It seems like the best bet might be to have a bunch of small jobs, right? And they stop quickly, and you just write out all your current data, and you start again later.
So the
what was like the challenge in like preventing from writing out the data, starting the job from where and pick up where you left off?
Yeah. So you go through a series of optimizations. You optimize both the structure as well as the charge density, basically where your electrons like to sit. And there is one optimization cycle that moves the atoms a little bit or the nuclei, and then it relaxes the electrons after that. And if you don't go through one of those ionic steps, you start from the beginning. And that ionic step can take, if it's a complicated structure, that can take a day on 30 nodes. So there are certain parts where you don't even want to stop the calculation because you've gained absolutely nothing. You've just trashed computer time. But I agree with you. If we could do that, that'd be awesome. But we have to at least get through one of those ionic steps.
So I'm not sure if this entirely is applicable to you, but do they use the same kind of theory when they design, say, like CMOS transistors? So like corporations like Intel, when they're designing, the next generation process technology for, say, low leakage, do they use this technology?
I don't know. They don't go to first principles codes typically.
They don't go.
No. What they do, they use continuum mechanics, sort of higher level codes typically, or even CAD, like to try to figure out where their materials should sit in the electronic circuit optimization.
Oh, so they're not trying to predict.
No, they're not designing new materials from scratch typically. No.
So like when they did the hafnium and all of that in there, that was.
That would probably be coming from somewhere else, yeah. Very few companies invest in first principle scientists. There are a few, but very few. It's coming along, though. I think we're showing through academia that this can work. So they're getting more and more excited about it, but it's unusual.
So there's no industrial best practices for this kind of thing?
No, I wouldn't say so, no.
Interesting.
No. So you work with different you can work with different kinds of queues. You can, charge more. That's one way of doing it. When we really need to get something done, you up the charge factor. But you have to consider the queue constraints, which are run limit, queue limit, and wall limit. And we're actually coming up against all three of them. We had more jobs than we wanted to run, we had longer wall times, and we had longer times that each of them wanted to do. And the checkpoint restart would have been great, but it doesn't always work. So I'm just going to tell you that these were all our problems. We've solved some of them, but we haven't solved all of them. We're still working around the queuing policies of NERSC. But let's say we did fix all these computing issues. What about the original problem, designing new materials? I would like to leave you guys with the feeling that this actually does work, and there's a reason we're still doing this. So I'll tell you a little bit about the kind of design material or projects we've done in the past. And the first one was on alkaline batteries in 2004, and this is how it all started. Duracell that makes these little batteries, AA batteries. They're manganese dioxide, and they have a core of zinc powder, and they have a very, very alkaline electrolyte. If any one of you have ever opened these up, don't use your fingers, it will burn. You look like you've done it. This is a very old technology, and Duracell, that is owned by Gillette, the razor blade company, that is owned by Procter & Gamble, that pretty much owns everything as far as I can tell. They make a lot of money on these little dudes. This is a very old technology, but they've been doing it for a long time. If you ask them how much one of these costs to make, they won't tell you because it's kind of embarrassing, but they'll throw a nickel on the table. So next time you go to the supermarket and buy a few of these, think about how much money they're making for Procter & Gamble. Anyway. So much for the politics. They were a bit worried, though, or they're still worried, because this is an old technology, and they're wondering maybe our competitors like Energizer, maybe they're working on something better than this, because it's been around for a long time. And I was at MIT at the time, and we were doing batteries. We had never done any high-throughput computing of batteries or cathodes, but we were kind of thinking, if we can do this for one material and we have more computing, and we can do it for more materials and we could get better. We knew how to calculate a lot of the properties that were interesting for batteries. So this tells you, for example, how the discharge curve goes in a phase diagram if you were to predict a new material that's AbO4. If you discharge it and you release, you absorb a number of electrons, how much capacity and what would the voltage profile look if you're starting out with that AbO4. So we knew how to do all these things, but we had never done it for thousands of materials. So Procter & Gamble, or Duracell, came to us and asked, what would it take for you guys to screen all of nature? Every material that's ever been known, if that was a better drop-in replacement for manganese dioxide. They wanted to keep the zinc and they wanted to keep the electrolyte, but they wanted a better cathode. And that's when you swallow and you go, $1 million in 1 year, which we had no idea if that was sufficient, but we just threw it out there and say, let's hope that it works. And it actually did work to some degree. The one thing that we stumbled up against, we were very good at predicting the solid state materials properties of these cathodes. But we had never looked at the corrosion, the dissolution problem in this very corrosive electrolyte. It turns out that manganese dioxide is one of the few systems that work. This is the experimental, you've seen this again, this is the Probet diagram, I love these diagrams, goes between manganese dioxide and this little sliver here, which is actually manganese oxyhydroxide, even at pH 15, which is where we are in these cells. So again, outside the pH chart. It's more KOH than water in these little cells. It's very viscous. So we had to come up with a way of screening for the dissolution of solid materials at pH 15. And we actually did it by combining two different data sets. We used our computed solids with experimental aqueous ions, because aqueous ions are really hard to calculate from first principles. And that kind of worked. So our calculated Probet diagram is the one here, where we actually do better here than the Probet's one, but we miss a little sliver of the Mn203 or Mn304 over there. So we could now we could calculate the solids, we can calculate the capacities and voltage and all the different properties that were interesting, as well as the dissolution. So we took all the known inorganic compounds in the world. It's about 30,000 of them, between 30 to 50,000. And you can permute them, right? You can substitute in different cations, you can swap chemistries, you can change them in different ways. We started on day one not computing 100,000 of them, because that would have been stupid, right? We computed about 2,000. We learned from that. We suggested new candidates. We data mined it. We went in cycles. We honed in on the chemistry spaces and structure spaces that became more and more promising. And in the end, when you've run the cycle over and over again, you come up with some candidate material that you present for the client. what do you learn by these sort of data mining? What do you learn by looking at lots of data? Well, one thing that we learned is how to design stable solids with very high energy density. They were looking for things, well, I want nickel 4+, I want manganese 5+, 6+, I want bismuth 5+. These things are very hard to stabilize in an oxide. They tend to, in binaries, they fall apart. They don't like that. So you have to add other cations, and these green spaces tell us where we have lowered the formation energy by introducing another element into the compound, like calcium, potassium, lithium. And it turns out that these low-valent, large, fluffy cations, they really stabilize the small, high-valent, high-energy density cations. Another thing we learned was that pretty much everything dissolves at pH 15. The blue here is the solution driving force. So you don't want to use the things that are over here. This happens to be, I think, phosphorus. Really terrible. But there are white areas. So there were cations. There were elements that were more resisting to this dissolution force. And they tended not to be redox active, but by introducing a small amount of them, we could, to some degree, protect the material against the dissolution driving force. So as a summary, we went through 130,000 compounds, which was a factor of 100,000 more than most people had ever looked at. And 30,000 of them were known, but 100,000 of them were sort of permutations that we had come up with. 1,500 of them were better than manganese dioxide in terms of energy density, either by voltage or capacity. But only 200 of those were even remotely stable, and we were generous on this because, you know, it was a tough problem, remotely stable in the electrolyte. These are some of the patents that were filed by Duracell, bismuth 5 and nickel 4. They're working on the nickel 4 one. The bismuth one came upon a bit of an obstacle. So we actually screened out 2 expensive elements. We didn't even put gold in our optimization or platinum because, you know, never going to work in a consumer battery like this. But bismuth made it in because bismuth actually isn't very expensive. But it has a very low global production. It's one of those elements that's produced along with something else. It's a sort of a side element that is not mined directly. There's no domestic production, absolutely none in the US. And the lawyers at Procter & Gamble, once they found out that one of our most promising elements was bismuths, they made a quick calculation and realized that they would have to buy every single bismuth mine in the world to make this happen. So the bismuth was out. They could have made that optimization beforehand, but they didn't. Although the nickel is still going strong. Anywho, at the end of this project, okay, who recognized this scene? Again, you can see, you know. Well, it's the end of the first Indiana Jones movie. The first one. Okay, so again, it's the same time era. You know exactly how old I am now, as the Back to the Future one. It's when they wheel in the Ark in the large warehouse and they never see it again. That was pretty much how we felt at the end of this project because it was a great project. We were super enthusiastic about the fact that we had actually predicted new materials and some of them were working to some degree. And we never really knew what happened to them afterwards. I am actually talking to Duracell again now. They're coming back because that nickel compound that they were mostly excited about, it kind of works and it's twice the energy density of these little dudes. They have a few problems with it though, so they want us to again calculate and see if we can help them. But we could never publish any of this. We could never bring any of this to the public. So we wanted to do something different.
So the 15 to 18 year projection still may hold?
Yeah, okay. It might. They're still working on it. So, you know, it's, we'll see if we can break it. So we took the same idea to MIT, and this time we sold the same idea to 2 other companies, Umicore and Bosch. They wanted to look at new cathodes for lithium-ion batteries. And I'll just tell you, lithium-ion batteries kind of work this way. You have a cathode that tends to be a lithium-containing transition metal oxide. You have an anode that's typically today carbon or graphite. In the very old days, it was lithium metal, but it's very unsafe, so you don't want to use that. And the composite electrode looks something like this, where you have active material, like little particles that are gunked together with carbon black and you know, other kind of stuff. And the real material that you look at, that we calculate, this is this part. It's the actual sort of where the atoms sit and where the lithiums shuttle in and out of the layered. They're not all layered materials, but some of them are. A lot of them are. And a lot of the materials properties, again, that we are interested in can be computed. voltage, safety, lithium mobility, and structural stability from that phase diagram. So we took the same idea. We now had an infrastructure, at least the first guess of one, that we could automatically compute things on our cluster. We can put them in a database. We can analyze them. We can suggest new materials. This is a graph of how many we went through from January 2008 to July 2009. So about 20,000 materials were calculated. This is, again, on our local cluster at MIT, not a shared resource, because we didn't have to deal with, in those days, we didn't know anything about how we could deal with those kinds of problems. So this was all run on an owned machine. This is a chart, a space, which shows you all the different materials that we computed, voltage versus capacity. And energy density, which is one of the parameters you want to optimize, is how much energy is contained in the cathode, or how much you can get from it, is voltage times capacity. So voltage tells you the sort of price of the electrons, and capacity tells you how many you can get. So it's the product between the two. So you'd really like to be out here, right? Because that would be really high energy density. But it turns out that there are other constraints, right? It's a global optimization problem. Things with very high capacity, if you try to shuttle in 3 or 4 lithiums, usually the structure falls apart. It can't handle that because you need it to be stable on both endpoints, fully lithiated and fully delithiated. If you go too high in voltage, you break down your electrolyte. You just can't stand the voltage gradient between the anode and the cathode being higher than about 4.5. Then the organic solvent starts to fall apart. It just can't hold up anymore. So the sweet spot for new materials tends to be around here. Not too high capacity, not too high voltage. So it tells you something about the trade-off in different properties that you have to go through when you want to design new ones. And this time I can actually show you which materials we came up with, some of them at least, because they've been published, because this was a public, or at least a university-backed project. This is a new vanadium phosphate, and this is sort of the real battery data. It has never been seen before in nature. It was designed by us. This is a whole class of materials that we call the siderenkites. They're lithium transition metal carbonophosphates. And again, if you talk to a battery chemist, they would look at that and go like, what? Because they have never seen a carbanophosphate being suggested as a battery material, but they do work. And they have a cute safety feature. If you heat them up, they don't release oxygen, which is the mechanism that burns the electrolyte. They release CO2, which is a fire extinguisher. So it's a good material that way. So that was the MIT project. Now we're at 2008, and I have moved from MIT to LBNL. And one thing that we realized when we were doing all these computations, that a lot of the properties we were computing, like material stability, materials energy, diffusion, could be used for other things than just batteries. And we had them all sitting around in a database. So we thought, why don't we give this to other researchers that do other kinds of problems, that maybe do photovoltaics, thermoelectrics, the platinum problem, the catalyst problem. So any of the things that are materials dependent and that I talked about in the beginning, we need better materials. Maybe we can aid those researchers, and maybe not just computational people, but also experimentalists who can't do these computations. So we started the Materials Project, which is a public resource. And the Materials Project basically aims to fill in that missing property data that we talked about in the beginning. If we knew more about the materials up front, then maybe we can design better ones. Assist researchers in predicting new materials, provide interactive analysis tools and codes. You can check it out, www.materialsproject.org. You'll see, and I'll show you some of it. You'll see that we have tried very hard to be user-friendly. So you guys who are not material scientists, tell us if we are. You may give us really good feedback on what we need to do better. And enable rapid screening and data mining. So basically being able to scan through thousands of materials, search for different properties, and slice the data in different ways and try to understand which chemistries and structures correlate with certain properties. This is what it looks like. We actually recalculated a lot of the materials that we put in the database. We didn't take the ones we'd done on the consulting because we actually wanted to do it a bit better. You tend to do it a bit on the fly and fast because when you know what the problems are. But when you put it out as a public resource, you want to do a bit better. So we recomputed them a bit more carefully. Right now, this resource contains about 30,000 materials. And we have different ways of slicing the data, different apps, because we try to attract the young viewers who are out there. And they're all free. So there's a phase diagram app where you can look at the phase diagrams of these materials. There's a crystal toolkit where you can manipulate them, you can substitute them, and very soon we're going to make it available to also submit a calculation, so do computations on demand. So you can substitute the material, maybe that you found in the database, or your own for that matter, and then have that computed. We have a lithium battery explorer that I'll just show a little bit more about. We have a structure predictor, which we use ourselves, which uses these correlations between chemistries and structures to suggest new possible candidates. Materials explorer and a reaction calculator. The structure predictor we thought was going to be sort of something that only computational people uses, but it's actually one of our most favorite apps because it's actually, so far as I know, the only publicly available new compound or structure generating algorithm out there. There are lots of researchers that use similar things, they have substitution codes, but this one uses data mining of existing known structures in the world or that are known and try to find correlations between the structure and the chemistry. And if you then give us a new or some sort of composition, let's say we want to do vanadium, zinc, and oxygen, then we use the algorithm that we have and it's done on the fly and it's private, so it ends up in your account. And we give you a list of the different stoichiometries, the different formulas, and the crystal structure, and the XRD. So in the case, this is for an experimentalist, if they make it, they can match it up. The lithium battery explorers. Now we come back to the 787. Actually, the reason that the 787 battery thing went the way it did was, I think, an electrical circuit problem, but it ended up heating up the battery, which was overdimensioned. It was too large, and that's how it ended. But that gives you kind of an idea that you can't heat up these things. If you leave your EV in the Arizona desert, either you come back and your battery is so discharged and you will probably never be able to drive the car again, or it might even catch fire if it gets really, really hot. So these things are sensitive to heat. This is why the Tesla has a cooling system on on the whole battery pack. And one of the properties, so this is how the Materials Project presents the battery data for all those 400 battery compounds that we have computed. Each of them have a page like this, where you have voltage curves, the structures, the capacities, the reactions that they go through, stuff like that. And we also show the oxygen release curve as a function of temperature, because that's the thermodynamic property that correlates with the safety of the material. If you heat it up and it easily releases oxygen, it's unsafe. That's how they all work to some degree. This is a nickel phosphate. There are still people in the world working on this material to try to make it into a battery material, or try to implement it, because it has a perfect voltage profile, really high energy density, but it's totally unsafe. It bubbles at room temperature. So it's just no way you're going to make this work. This is the one we came up with, one of them, the manganese carbanophosphate. It's a bit better than that one, and it releases CO2 first. This one is the best one known so far that is actually commercially used. It's lithium iron phosphate. It has a much, much higher tolerance for temperature until it releases oxygen. So that's one way of using the lithium battery app, that you can compare the different materials and their safety aspect. At the last part, I'll just want to show, because you guys are, computational, or you're computer scientists. This is how the infrastructure looks like, and it's not quite as messy as this plot is. I haven't been able to get my people to do a better one. When either they do something that looks like this, or they do one that is just 4 arrows that goes in for some reason we've never been able to come up with a better version. But we have a database that kind of sits as a spider in the net, and everything goes back and forth, and the computations are run from the database. It talks to the manager at NERSC when you have run, and our workflow is called Fireworks, and it launches rockets, of course. We have an automation engine, message queue. We have a library called PyMetGen that I'm going to talk just a little bit more about. It's a publicly available code that does all the analysis and produces all the input files. So if we start with the structure, PyMetGen analyzes it, spits out input structures for our DFT code. What comes back from the DFT code from the Schrödinger equation is then analyzed again in PyMetGen, goes to the web UI and can be monitored and looked by people. Then we also have something called the Materials API, which is a free way directly into the database where people can draw lots and lots of data directly without going through the web UI. So we've tried to build something sustainable. In our line of work, we know that no code is more long-lived than the student. I don't know if that's true for you guys too. So PyMetGem being a public resource, we have tried very hard to make it something that it will actually be sustainable. Everything, some people are actually coming in and contributing new code to it, so it's becoming a bit of a freeware system. But everything before it's introduced into the master branch has to come with unit tests, it has to come well documented, and we don't accept variable names like Depeche Mode or something like that. It has to say something about what you're actually computing. So we're trying, but we're material scientists and not computer scientists, so it's a bit of a learning curve. PyMetGen, though, it was launched freely. We had been using it for a while, of course, but it was launched freely in October of last year. And we've had 400 downloads, and obviously a lot of people on the West and East Coast, but there are people in Australia. So hi to you people in Australia, if you're online. You are using PyMetGen, some of you. This is the Materials API. It's, I didn't know that Google and Netflix and all kinds of other places uses APIs, but when I found out that they did and that we could use it too, that was pretty cool. It's basically a way of going directly into the database and extracting lots of information, which isn't what the UI, the web UI is built for. When we have these sort of user-friendly things where you can get 10 materials or 20 materials. If you want to get 20,000 materials, this is the way to do it. And we've built that into our framework as well. And why do we do that? Well, we do it because people do things with data that you can never imagine. The web UI is something that we have come up with. It's our way of slicing the data, of looking at it in a certain way. And if you give raw data to people, they do all kinds of creative and cool stuff with it. So we enable basically the raw output from the database, from the Schrödinger equation, from our runs, and people can do whatever they want to. And whenever we have collaborators working, for example, those students, on trying to come up with a better algorithm for understanding the runtimes, then they, of course, use the API to draw those 2,000s of materials records that they wanted. This is what it looks like right now. We launched in October 2011. We have 3,600 users registered. And I'm hiring a web developer. She's coming in a few weeks. When we told her that we had 3,600 users, she looked a bit disappointed because, she comes from the world of Twitter and so. But for the scientific community, this is pretty good. In a year and a half, we have grown from just the 2 partner institutions of MIT and LBNL to a lot of other companies, or not companies, but academic institutions have joined. And some of them are raising money themselves to join us, and some of them we are funding directly through the DOE grant that we got. So I'll just end with my vision of how this is going to help people. This is how the scientific community typically works, at least in my field. We are all our own individuals with our own toolboxes, and we're experts in a certain field. And we tend not to go too much outside of that comfort zone. When we try to make up new inventions, we do it within the comfort of our community or our own expertise. But if we bring more data to these people, if we bring data that has been computed by other people, then hopefully we can stimulate them to use these toolboxes on other chemistry sets and other spaces out there. And I say towards the materials genome. That was actually the name of our project when we started. It wasn't the materials project, it was the materials genome project. But then somebody else thought that was a really cool name. We were asked by the OSTP, not by Obama himself, but the OSTP that, can you please give up the name because we would like to launch an initiative with the materials genome as a title. And what do you say, right? When the government knocks on your door and say, we'd like to fund things that are exactly in the spirit of what you guys are doing, you would say yes, of course. So we dropped the genome name and we became the materials project. And in 2011, I think 100 million went out in that initiative, and we actually did get funded through one of the proposals we sent in, so it's good news all around. And we were recognized as one of the first of its kind sort of search engines that hopefully will speed materials research along.
Did you consider the name
Did you consider the name Facebook for molecules?
Well, we already have a little part. If you ever look at up our website, there's a little thing up to the right, upper right, that's called Moogle. So we're probably going to get sued already by one of those giants. So let's not push it even further. So Moogle does basically a little search, the same spirit as Google over the materials. If you write phase diagram, lithium iron phosphate, it will direct you to the phase diagram map. So we're trying to keep up with the times. I think that was my last slide. So if you guys have more questions, discussions, I'd be happy to answer.
So do you have class projects to suggest perhaps for next year?
Yeah, absolutely. I mean, so the thing that the students were doing, that was largely unsolicited, and I think just David Skinner, who I work with at NERSC, he just suggested it and they're doing it. That's one of the ways we could, you could interact. And again, the data is all out there. You can even play along with it on your own and see if you can do something with it, and let me know. Trying to predict runtimes is definitely a really important problem for us. It's still a problem, even though these guys seem to be doing okay. We still have lots of problems with trying to fit into the high-performance computing policy queue. So
in addition to the output data being public, is the computational code also public?
the DFT code, you mean?
Yeah.
No.
Okay.
It isn't. So VASP is a commercial code. We tend to use, there are some that are public. The one we're using is not.
What's it called?
VASP, but with a single V, not WASP, VASP. There are public ones. We are going to branch out and do some of our computations with them as well. The problem has been that this commercial code has always been a bit better. It is being developed by a university though, but they're making money on it.
So is all the parallelism in your system inside of VASP?
They have it inside there too, but you can try to do it yourself too. You do get the code. When you pay for the license, you get the code. But it's a pretty nasty code to try to change.
There are a lot of other folks who work on parallel DFT codes,
yeah.
but I guess they're not appropriate for your particular application?
So some of them I know are for much, much larger systems, and they tend to use real space. So if you do like 200, 300, 500 atom nanoparticles embedded in something, then yes, those work better, but they tend to sort of coarse grain certain part of it and not and solve better on other sides of it. So it's sort of a, yes, it's a different kind of problem.
And so how many atoms in your simulation?
So we tend to do up to about 300. After that, we get choked down, but it just takes way too long.
Okay.
Could the data that is available be used to predict runtime? Does it have job information and other context from the running simulation?
I believe it does, yes. Should be in there.
Okay,
Yep.
on a per job basis?
Yeah,
Okay,
yeah,
that's great.
yeah.
Thanks.
Just curious about your infrastructure. Do you have a means for external collaborators to request new jobs be run to explore new materials? I mean, it sounded like you did sort of there in one way, but is there a programmatic interface to that or just the web interface?
So right now we're working on getting it on the web interface. So sort of to be a button, submit a number of jobs. We are bundling it though, so you don't have to click for every single job you want to do. So if you want to submit, like, for example, our partners within the collaboration, those universities, they're going to submit thousands of jobs. So they'll use the same capability, but they may not go through the web. So yes, on both accounts, both for the people who just want to submit one through the web UI and one that they might do. But it's not up yet, but it's coming in a few weeks, I would say. Yeah. I have to say, though, that at this point, if we're doing it, the people have to show they have a license for VASP. Unfortunately. We can probably do a bit on, no, I shouldn't say that. Why should I? But yeah, no, that's, yeah. Okay. Thank you.